Şunu çıkartmak gerekiyor.
Let's continue. So we were talking about the diffraction note, and I think we pretty much discussed many things about it. Another mode is high resolution mode, and I'm not going to go into the details of how it really works, but what it does is actually starts using the phase information stored in the transmitted feed, not only the intensity, but the phase, which is basically used to construct the diffraction pattern. And by combining these two, you can create a very detailed map, so detailed that it has atomic resolution. If you look at this is like 5 nanometers, and the things you see here is the basically iron cores. The scattering from the electron cloud is much more smaller compared to the host of the ions. So what you get is atomic resolution.
What is primary?
The primary beam is the main beam that is transmitted through the surface. It's the beam in the bright field. So it's a gray beam is the primary. And it combines it with the diffraction data. Now, if you think about it, it makes sense, right? We have diffraction data. So from here, we can resolve the crystal structure. The information is there. And this tells you which parts are absorbing the electrons most. So by combining these two, you can create a very detailed image. You have atomic resolution. And you can go down to 0.2 nanometers. And in state-of-the-art TMs, actually, there's a company in Seattle. They were building these TMs, and they could actually identify each and single atom on an image. Of course, the TM is a $10 million TM. What's that?
How much you want to use?
It's about 3 million. And it's not state of the art. No,
It's the cheapest.
it's not cheapest. You can buy the TEMs for 500,000 euros, but it's no different than MSC. It's just more looking very simple stuff and very low magnifications. If you're nowadays after a state-of-the-art TEM, it's like 3-4 million euros. So show some respect. I can go downstairs. Next slide. Honorable issues. But yeah, I've seen that guy was visiting the University of Washington. He showed EM images that were so detailed. They were looking at this graphene plane, and they replaced a few of the carbon atoms with boron, and they could like distinguish boron atoms in those carbon chains. They had that high resolution. I wish we had one here. Right. Any questions about EMs?
Yeah.
You have a sample, a fixed sample.
than 300 nanometers, don't
Yes.
use a TM loop, you won't be able to resolve it. Or you need to, you have to use SEM. But then in SEM, yeah.
So
If you're using TM, you're after high resolution. Or you have a biological sample that you must see which parts are different.
what about the mode? Does the mode
Yeah.
change when we have feature sounds?
Well, all the modes have limitations. If you have a very thick sample, let's say you want to take diffraction pattern from a sample which is coated with a polymer, forget about it, it's not going to work. If you have and polymers are nasty stuff. If you have 500 nanometers thick polymer, it's not going to work. If you have few polymers, few molecules of polymer, maybe. But typically, if you're really after this high resolution, you need a perfect sample, very thin, very clean. Otherwise, what you get is just cloud of blurriness. You don't get this high resolution. And if you go to SEM now, it's a totally different story. You cannot even imagine going down to these resolutions.
Maybe you have talked about it, but my question is there any specific sample preparation for TM and SEM? I mean, not more about TM.
So, yes.
Very great
Yeah.
time.
I mean, it depends on what kind of material you want to study. If it is like a biological sample, there are different techniques. You embed it in a polymer matrix or things like that. You take slices out of it, very thin slices, few hundred nanometer thick slices. We have a machine called ultramicrotome, which takes very fine slices. You put it on the TM lid, you go downstairs, it goes fine. If you want to look at a cross section of a plane material, you use FIB. You take cuts, as shown here. You take a slab of your material, flip it sideways, attach it to your TM grid. You get your sample. In our case, we're dealing with 2D materials. We transfer this whole 2D crystal to a TM grid.
So FIB, the roughness after FIB, that you get is because for like metallic components, like polishing, like electro polishing gives us nanometer roughness.
So in the case of FIB, typically you don't have any problem in terms of sidewall flatness. There are sometimes gallium penetration into the sample material, but you can always find regions without gallium penetration because what you're interested in is extremely small region, and you can always find flat sections of your sample. You don't need to actually polish your sample. But in the case of their methods like, especially if you're not interested in fine details, but in bulk sample, then yes, there are different ways you need to know for polishing. It's again a whole different business. Preparing TM samples is really an important aspect of using TM. Any other questions? Okay. Scanning tunneling electron microscope. Again, we are at the boundary. After this, I'll start talking about scanning probe microscopy. So this is the interface. You can put this in both scanning probe microscopy or electron microscopy. It's an electron microscope technique because what happens is you have your sample. It's under bias with respect to the tip. And then you have an extremely sharp tip. It's much more sharper than the event tips. Indeed, at the apex of the tip, you have one or two atoms, it's that sharp. AFM tips are much more dull compared to this. And tips are typically made of tungsten, platinum, iridium alloys, and again, they're very sharp. And what you do is, you bring this tip very close to the sample, so close that actually in the first midterm, you sort of solve the question related to this. It's so close that electrons from the metal start tunneling into the tip or vice versa. And this tunneling strongly depends on where you have electrons, electron clouds, right? If you don't have electrons here, then the tunneling rate decreases. So you get two things with this. One, you get topography of the surface. Of course, it should be extremely flat, otherwise it's going to be affected by that surface roughness. And STM sample perforation is an art by itself. But you can get some information about topography. And this information is useful because you want to maintain a fixed height from the surface so that the tunneling rate can be kept at a certain level. And what you do is, based on the position, you measure tunneling current, how much electron jump from tip to the sample or the other way around. And this gives you a very high detailed image of the surface. This one is a carbon nanotube. If you look at it, actually you can see that it's twisted. The roll of the graphene is folding itself with an angle, so you can see these carbon chains twisted. But it's a single wall carbon nanotube. And each bright spot you see here corresponds to a carbon atom. So you have atomic resolution. I think in this case this is a gold surface. So again you see these gold atoms forming a nice uniform crystal. So I'm going to talk more about how actually you control this tip and so on, because it requires a feedback mechanism so that we can keep the tip at a certain height. There are various different preparation modes, but I think what matters is the idea here. Now, again, if you go back to the parts of the lecture where we studied quantum mechanics, quantum tunneling was something hypothetical, which came out of equations. But here, this uses that technique only with electrons, uses that principle, and you can get down to level resolution. Of course, this has a limitation. Your sample needs to be conducted to a certain point, otherwise this bias is not going to work.
Sorry, I didn't get one. Does it tunnel from tip to sample or from sample?
And now you have higher potential in the sample. Okay? So electrons want to tunnel from tip to sample.
Let me detect that.
And electrons are coming from here. So you amplify the current. So the current is going actually in this direction. Electrons are going in the other direction. You amplify that current. And based on that, this distance control and scanning units completes the feedback loop and adjusts the height of the tip. Any other questions?
If the sample itself is not conductive, can we, for instance, coat some metal like we do in SEM?
I don't think this will work nicely because now when you have this coating of metal, so you will be measuring this coating from that metal. You will have topography of the sample to construct, for instance, band diagram to a certain extent. I want to observe a couple of the momentum as also that there are uses of SDM. All right. Scanning probe microscopy techniques. Now we are shifting from electron microscopy techniques to scanning probe microscopy techniques. The idea is the same as before. SDM. You have a very sharp tip. Tip is typically 10 nanometers wide. You can see that the scale there is 100 nanometers, so it's like, this is a little on the other side. This is like hopefully 14 nanometer. That next tip. Nevertheless, it's a very sharp tip. And then you have this cantilever. So this tip is attached on the underside of this cantilever. And then what you do is you have this laser shining onto the upper side of the cantilever, and it reflects to photodiode quadrants. So what happens is, on the normal operation, there is no deflection of the laser when the cantilever is flat. The laser beam just hits the middle of that photodiode. When you lower this to the surface, because of certain interactions, which we'll talk about later, the tip starts flexing. And this flexing results in deflection of the laser. And by that deflection, you can create a map of surface, because when you reach a flat region, there will be no deflection. When you go through a bump, there will be deflection. But this will allow you to create a surface bump map with very high resolution. There are, by the way, this SDM and AFM got Nobel Prize in 1986. Did they get? I'm not sure. Okay, so I don't know if you were here. It was 2015. We invited Christoph Gerber. He was one of the inventors of the AFM, and he was here for the Nano Day. And I don't know why he wasn't included in the Nobel Prize, but he was very close to getting it. He was in the team for some reason. They included him more than the Nobel Prize. And there's an interesting story that I want to share with you. This method, you shine laser to the tip, reflects prototype. In one of our projects, we're designing a custom-made stress chip where we need to measure very small deflections of one part of the chip. So if AFM can do it, we can do it as well. We shine a laser to the side of the chip. It reflects back, and even if there is a 0.1 nanometer change in the gap of this paddle, the laser gets deflected, and we can measure that deflection. So I explained that we were inspired by this concept from the AFM. I told it to Christoph. I said, I don't know if you were involved in that particular part of the AFM invention. He said that patent belongs to me. So I used his patent without knowing me, but it was a nice man. He made it easy. Whatever. There's this, 3 different modes contact mode, tapping mode, and non-contact mode. And each mode, of course, I mean, these drawings oversimplify things, but there are many complications when you actually look at the real thing. First of all, this measurement is an extremely noisy measurement. So what you do is you vibrate the probe at a certain frequency. You drive it at a resonant frequency. And since you know that frequency, your signal is modulated at that frequency, and you use that information to infer that how much deflection you get by using working techniques. So I'll talk about that in more detail. But this is typically how it works. Let's talk about contact mode first. You have this tip. What you do is, as the name suggests, you lower the tip to a point where now it's in contact with the surface. Okay. And this is an aggressive technique. Your tip needs to be hard. It shouldn't be a soft material. And your sample needs to be hard. And this technique is heavily used by friction and releasing forces. So nowadays, I don't know, not many people use contact mode. We use it from time to time to measure the thickness of atomic layers. But really, contact mode is something that you should stay away here.
Doesn't it damage the sample?
Yes, it damages the sample, it damages the tip. It's avoidable. It requires a lot of patience and experience, because if you press the tip too hard on the surface, then you just start scratching your sample, especially from 2D stuff. They're so fragile. You think that you're scanning just bare surface, but actually you have something that happens is you scratch your surface, your sample itself. So your sample needs to be hardened brutally, but then you adjust the force to a point where it barely touches the surface. Then you may get some. Another useful mode is tapping mode. Actually, this is what you use mostly. What you do is you modulate the tip at a specific frequency. As it's a cantilever, there's a natural frequency, so there's this resonance frequency. Okay? And you drive the tip either at that frequency or slightly shift it, like somewhere around here. Okay? And what happens is, as you bring the tip close to the surface, because of the interactions, you change this natural frequency of the oscillation. Is this clear what I'm talking about? We have a beat, and it has a natural frequency of oscillation. If you drive it at that frequency, it's going to go into resonance, and it's going to start oscillating at a very high amplitude. That's what you're seeing at that F0. It's going to be oscillating at a very high amplitude. But as you get close to a surface, what happens is, due to interactions, you tune this resonance frequency. Now it's shifted to somewhere else. And since we're driving it at a slightly shifted frequency, we can detect those shifts. They're very fine detail. And this information, combined with the deflection of the laser, we can resolve what's going on at the surface. Of course, there are many things you can adjust here. You can adjust where you drive your cantilever. You can adjust the amplitude you drive, the voltage. There are many things that you can adjust to get the resolution. Like here, I think it's that scale is like 25, and you really have very high resolution. I think these are some proteins, and I don't know how to get this. I usually do reference. So, I mean, you would think that these proteins are loosely attached to the surface, and they are. But the tapping mode is so gentle, that kind of stuff, that it won't drag these molecules around and doing the scan. This is useful for scanning very fragile stuff. And this study showed the effect of pH. Stuff like this. What's that? Yeah. Clever stuff. Another mode is non-contact mode. You do this oscillation, the one that I've shown, at a place where you have no contact. So the oscillation takes place at some height above. This time the tip doesn't touch the surface, so it sort of uses long-range interaction. So if you look at this diagram, it shows what happens when you really get close to the sample surface. What happens is you have attractive forces to a certain distance, Van der Waals interactions and so on, and they increase to a certain point. But once you pass a certain point, the forces become pulsing. And in contact mode, that's what you use. You're in repulsive region, the surface tries to repel your tip. In non-contact and tapping mode, you're still in the attractive force region. But in the case of non-contact mode, you should be careful because, for instance, in certain cases, especially when you're doing AFM on vacuum conditions, water molecules cover the surface of your sample, and your tip gets affected by that water film. I don't know, imaging that. Non-contact mode is not, again, for non-experts. So that's why when you get trained for AFM, you learn tapping mode. It's the easiest method so far.
What about browning motion in liquids? Should they move while we're scanning? When we scan, we solve it, but they're kind of liquid, right?
No.
Did you say that?
No, there's a water molecules on the surface of your substrate. So it's not like your stuff floating inside the water. It's just water molecules attached to the surface of your stuff. It's not like a tiny drop that's floating. It's a very thin layer. It's a very, very thin layer. It's only a few nanometers. And you can see its real effect actually. Scan. Very interesting. Not in AFM, but there are other techniques that we discuss, like electrostatic force microscopy becomes very important. Now,
Yes.
yes.
Regarding precision, which one is more precise? Which mode of shading?
As I said, contact mode and give you better details for if you're trying to resolve very fine features. That's an aggressive technique. It may destroy yourself. Non-contact, I believe, it is the least sensitive because you're not even touching the surface. You're depending on long-range interactions.
But for tapping mode,
There's an intermittent contact. It's constantly touching the surface.
what do you mean by constantly? I mean, what's the difference between those tapping, yes, and those tapping?
So it touches and then goes up, touches and then goes up. And this happens at 200 kilohertz. So it happens 200,000 times a second. But it's enough to keep the tip far away from the surface. And the amplitude of the oscillation is not very small, it's actually considerable. The amplitude is like a few nanometers. So you're really touching the surface and moving the surface 200,000 times a second.
So frequency is high enough to detect all of those.
Oh, yeah, yeah. And your scan rate is like, what? Tens of nanometers per second. And you already touched 200,000 times within that interval. Definitely much, it has much higher resolution than you can ever scan. Even if you do the scan very slowly, still you will have much higher resolution. It's a very robust technique. Like, here, optical microscopy images of various 2D materials. Here you have graphene, and this square here shows 4 layers, 3 layers, 2 layers, and 1 layer of graphene. And you can observe the level differences between layers. Like MOS2, 1 layer, 5 layer, 4. Average diselenite surface, 2 layers, and so on. Or nitride, again, you can observe different layers. And look at the scale bar. Not because I haven't given it. But this is on the order of like tens of microns. So the scan size is like 10 microns. And in that 10 micron interval, 10 microns is large region of stuff. And in that 10 micron screen window, you can get height differences of 0.3 nanometers, 0.6, 0.7 nanometers. It's a very robust technique that can be applied to various samples. All right, now we'll go into variations of atomic force microscopes. Like one variation is electrostatic force microscope. And it's like not like an SDM exactly, because there's no tunneling involved. But what you have is a cantilever that's held at a certain potential. And then you have a sample that's held at other potential. So there will be some electrostatic attraction. And the significance of this technique is that, for instance, if you think about PN junctions, we're talking about built-in electric fields and localized electric charges. This technique actually allows you to visualize those. Because think about it, you have a PN junction, two materials go together. Now you have ion cores, positively charged, negatively charged. So you have really positive charges on one side and negative charges on the other side. And using this technique, you can do a scan and see which parts are positively charged and which parts are negatively charged, down to resolution of a few tens of nanometers. So in that sense, electrostatic force microscopy is extremely useful. There are again two different modes of operation. You can do that at constant height, and this will reduce the effects of topography. One problem in these techniques is that topography of the sample will constantly interfere with this information. So you need to come up with clever techniques to exclude the effects of topography. So in lifted mode, you do the scan at a constant height. And at that height, topography has little effect because electrostatic forces are at a longer range than those forces at the near of the surface. So you can do that 100 nanometers far away from the surface. You get nothing from topography. And the only thing you get is the map of electrostatic charge distribution. Actually, Talip are used this a lot. For instance, they have these particles directly by wall, and they scan, they do a EFM technique, and they find where you have the charges placed. Okay. And then there's this constant deflection. This time you adjust the voltage of it so that the amplitude of the oscillation or deflection is kept same throughout the scan, and this in return gives you information about how charges are distributed. One advantage of this EFM is that you can measure principal the work function. It's again this is a list where it's commonly used. So it's a useful technique. What you can do is, for instance, you can apply, you make a single contact device, apply some potential here. That potential will start dropping throughout your sample. And let's say you have a defect. Around that defect, there will be charging events. For instance, we looked at tungsten bisanilide crystals. We put a contact on one side, applied a certain potential, and then scan the sample. And we observed that at gray boundaries, where we have crystals oriented at different directions, you get a very large drop in potential. That kind of things are possible with those specific force factors. One variation of EFM is Kelvin probe force microscope. You do this variation because to be able to measure, for instance, the surface potential of the sample, you need to exclude any interactions coming from topography and electrostatics so that you can find the work function differences between surfaces. Okay. Now, you have a cantilever that has metal coating, so it's metallic. And then what you do is, in the previous case, it was electrostatic. You didn't drive voltage on the cantilever with the AC, but here, what you do is, you drive the cantilever with an alternating current, alternating voltage at a certain frequency. And the energy of this capacitor, which is formed by the surface and the cantilever, is given by this expression. So the potential difference actually depends on the DC bias, contact potential difference between the metal coated on this surface and that surface. Remember, contact potential difference, if you bring two metals with different work functions together, they align the Fermi levels, and then you have now some part positively charged, some part negatively charged, but electrons can freely move around. It's not something that you can measure by applying voltage. But here, actually, it plays a role in the measurement. So the potential difference between the tip and surface is given by this expression. And from here, you can extract the force acting on the tip. There will be a DC component, there will be a frequency component, and there will be second harmonics on that frequency. By using this expression and this expression, actually you can extract the CPD, contact potential difference. Now, you know the work function of your cantilever, and from that information you can extract the surface potential of the surface that you're. It's a convoluted technique, but it's very useful, especially if you're studying new material. In this case, I think there are looking at ways to target different biomolecules to be attached on the surface. I forgot how they did it. It has been a long time since I read this paper, but if you're interested, go and look at it. So they can attach specific biomolecules by utilizing this word function reference. They can, without any labeling and so on, they can identify these biomolecules using change in word function.
Is that potential electrostatic interaction between just tip and surface? So what about the rest of the cantilever? Because I think if you take that into account, it would be difficult because it's not
Well,
between
this
the bonds.
distance is indeed huge. So probably the capacitance formed by that part is completely negligible.
What about the electrostatic interaction? Because when it come closer to sample, it changes. I mean, those parts which are
The body of the cantilever,
yes.
seriously, I mean, this distance, the tip is so sharp and so long compared to the interaction taking place locally here. It is completely negligible. Also, you're driving at a specific frequency, which allows you to isolate that. The rest. I don't think it's going to play any role, any measurable role. No.
For electrostatic effect, I'm not sure.
Seriously, it's not, I mean, the aspect ratio is like off the charts. The drawing here we seem like it's going to play a significant role. This tip is very sharp, and the separation between the body and the rest is huge. It's like microns, more than microns. Here you're dealing with tens of nanometers. Huge difference between these scales. So, even if there's some global effect, it's going to be this DC term, which is not going to be easy. Any other questions? Okay, another variation is magnetic force microscopy. This time, rather than coating with a metallic conductive material, you coated with a magnet, tipped with a magnetic material. So you have the magnetic dipole at the apex. And again, the same things apply to this technique as well. There are various modes so that we can get rid of topological effects on the surface. So you only have magnetic effects remaining. And this is, for instance, AFM height trace on the surface of a hard drive. Actually, this is a used hard drive, and you can see the scratches on the surface of the hard drive because of breathing. And use an MSN image. You can see each bit, each spin pointing up or down from this map. There are layers that separate each track from each other. So these are the actual bits that store the information on hard drive. And this technique allows you to do, again, imaging if you have any magnetic material on the surface of the cell. Okay. Now, another technique is scanning probe microscopies, near field scanning. This is an optical microscope. The idea here is to beat the diffraction limit by using near field optics. How is that possible? What you have here is cantilever again, but this time there's an optical core. It allows passage of light through. And what happens is you confine the light into that fiber, a very fine tapered fiber. The tip is typically, the opening here is like, I don't know, 50 nanometers or so, 30 nanometers. And light is coupled to this fiber and forced to go through the fiber. What happens is, it is a place that is much, much smaller than lambda, the wavelength of the light. Light leaks out, and then diffraction takes place. Where now your spot just immensely expands from that confinement, and we're back to this confinement region. But if you can bring your sample really close to this region, your all scattering and reflection will take place in the near field, and you can utilize that. You can construct an image, a very fine resolution image, using this thing. Now, here is the tip placed at different heights from the surface, and they have this PTB writing on the surface. And at 300 nanometers, this all blue. Look at the scales, 1 micron. So it's not a small image, but the details can be barely resolved. That would be very similar to the microscope. As you bring the tip closer and closer, the near field starts kicking in, and the resolution is much better. So with light, actually, you can have a very fine resolution. If you look at here, your resolution is, I don't know, like less than 100 nanometers. Much, much better than what you can get with an optical microscope, with a confocal microscope. Okay. So this is an extremely useful technique actually, because what happens here is you can use light to probe things at sub-resolution. The way to do it is rather straightforward. There are several techniques either they apply. They have a fiber, they shine a carbon dioxide laser while pulling it, and the fiber gets tapered, and then they coat sides with some metals like aluminum and gold so that they can form this waveguide. And then also there are these wet etching, chemical etching techniques. They coat it with certain stuff. They etch the cladding, polymer jacket, and then and then with hydrofluoric acid, they etch the inner glass core. They form this paper fiber. There are modes of operation. There is this transmission mode where you send the light from the fiber and collect the light from back. You send the light from the other side and collect the light from the fiber. The light can go from the fiber and collect it back. There are various modes of operation, both transmission, spectroscopic, and diagonal. And of course, the aperture, diameter of the teeth, plays a significant role in what we do. And if you make the diameter smaller and smaller, you lose a lot of laser power or light power. We'll continue this discussion of this next this Friday. So, yeah. Any questions? All right, and we'll see you on Friday. Yeah.